Hello everyone, I'm Bhattacharyya from Indian Institute of Technology, Kanpur. The topic of my presentation is experimental study of interaction of wall boundary layer and vortices that are shared behind a rotationally oscillating cylinder. Here we see the effect of forcing frequency at an amplitude of 135 degrees and gap to diameter ratio of 3 and Reynolds number of 250. Now this video on the left hand side now has an FR of 0.75 and the type of visualization is hydrogen bubble flow visualization. Now we'll see what happens when we increase the forcing frequency. And the forcing frequency is 1 when the cylinder frequency matches with the shedding frequency without the oscillation. And here we see what happens when the forcing frequency becomes 1.5. Now we'll see the effect of forcing frequency at an amplitude of 90 degrees and G by D 3 again and Reynolds number 250. So here again we have an FR of 0.75 and then we'll see what happens when the FR is increased to 1.5 and yeah, so the wake again the size of the wake reduces and there is no interaction between the wall and the vortices shared behind the cylinder. Here we have the results of laser induced fluorescence. We'll see the effect of wall at an amplitude of theta 90 degree FR 2.5 and Reynolds number 250. Now we have used laser induced fluorescence at higher FR because it yields better result than hydrogen bubble flow visualization. So here we have the no wall effect. Now we have the wall at G by D is equal to 2.5. We can see that the wall boundary layer is not interacting with the vortices shed behind the cylinder. Then when we move the wall close to the cylinder at G by D is equal to 1, we can see that the vortices shed behind the cylinder are strongly affected by the boundary layer of the wall. Okay, so here we see the effect of amplitude at FR is equal to 1. On the left hand side we have a wall distance of G by D is equal to 1 and on the right hand side we have a wall distance of G by D is equal to 2. Now the third figure from the left hand side shows that the wall and the wall boundary layer and the vortices shed behind the cylinder are strongly interacting and the vortices are the boundary layer is curling up and forming a third vortex layer. So instead of two vortices layer, alternating vortices layer that we see without the wall, we are seeing 3 layers of vortices. Here again we see the effect of FR at theta 90 degree. Again we can see on the left hand side we have a gap to diameter ratio of 1. On the right hand side of the image we have a gap to diameter ratio of 2 and we can see in the gap to diameter ratio of 2 the image on the left hand side, the bottommost image, we can see again 3 layered vortices. Again the wall boundary layer curls up and forms a vortex layer. Here we see the effect of wall at FR is equal to 2.5. We see what happens when we bring the wall closer to the cylinder and below we have at the bottommost part we have the no wall effect and we see how slowly after G by D 1.5 the vortices of the cylinder wake, it interacts with the boundary layer of the wall. here we have the result of three-dimensional span-wise mode, and on the left we have mode y at fr is equal to 2.75 and theta is equal to 135 degrees. We have the platinum wire kept at a upstream distance of 3d, and the span-wise wavelength of this mode is 2 cylinder diameters. Now then when we change the fr to fr is equal to 1 and amplitude 90 degree, we see the mode Z. Here the platinum wire is kept at 1 cylinder diameter downstream, and we can see the mode is having a span-wise wavelength of 0.6 cylinder diameter. So the wall does not have any effect on three-dimensionality. So that's it from my side. Thank you for hearing me out. If you have any questions, do let me know. Thank you.